a model of what you're going to do in the actual assignment. So this should get you ready for that. But I think the thing that the lesson doesn't maybe do the greatest job of is really give an example of what's even happening. I find a lot of students jump right to the assignment and they're like, okay, I'm kind of doing some math magic here and I think it's working out, but I don't really know what it means. So here's just a graphic of really what we're talking about with mass defects. And it's kind of neat to realize that this is actually true. If we had a nice little atomic scale and we could picture these protons and neutrons a little bigger, that we could actually handle them. This is what we could do. We could take the 2 protons in this atom and the 2 neutrons, weigh them individually, and these are the numbers we would have. We add all those up, and this would be the mass of the parts, is what we call that side. Now, if we kind of let them go back into their nucleus, see what's going on there, when they're actually bound together as a whole, if we weigh them now, they actually have a smaller mass. And the difference between those two is called a mass defect. And there's a reason for that. So we're not going to really spend too much time on the reasoning behind why. The focus of this assignment is really the calculation to get us there, to show us that. So kind of an overarching, that could be a way to think of it. An overarching kind of idea that you want to hold on to is simply that you can see that the parts really have a greater mass than the whole when they're all kind of clumped together. So here's another, this one's in question form, but it gives kind of that same idea, and it really kind of covers the fact that why this is happening, right? There must be some kind of energy holding this nucleus together. And we briefly talked about the 4 fundamental forces, one of them being that nuclear force actually holds the nucleus together. If we didn't have that, of course, we'd have all these random particles, but we have to account for the fact that there's energy needed to hold them together. So if we take the mass of the parts plus the energy that's needed to hold them together, which we call a binding energy, then the equation balances, and it equals the sum of all of the parts. And that's really what we're going to do in this assignment. There really is no equation for this. It's just looking at this basically addition relationship. The mass of the whole plus the energy needed to keep it together is equal to the mass of the parts. And if that's kind of a way you want to abbreviate it in your equation sheet, you can. It's just that it doesn't really have like a formal equation to go with it. Okay, so this is just a little picture of really why we're saying, well, there's kind of some mass missing there. We're really kind of swapping it out and counting that missing mass as the energy that's needed. And there's, of course, Einstein's equation to get us there. E equals mc squared allows us to say that that quantity of mass that's missing is really comparable to an amount of energy. Okay, so let's actually play with some numbers here. This one is helium. And so for helium, we have 0.030382 atomic units of mass that are converted into binding energy. So we could put that number right in here, and then our math will work. The 4.00150 plus the binding energy is equal to the sum of the parts, if I added all those little guys together.
And one of the conversion factors, actually this is probably one
I need to add to the equation sheet, is that one atomic unit is equal to 931.5 mega electron volts. So the M there stands for mega.
It's true that we could use
equals mc squared to also figure out the energy, but I'm really not going to ask you to do that or even use this equation in this assignment. So if you want to kind of temporarily set that equation aside, the more important thing to remember is this conversion factor, which I would say add to your equation sheet if you haven't already. And I'm going to make a note to add it to the one that I have posted because I didn't add it. And normally in an assignment, it's going to be given, but just in case, it's nice to have that reference. Okay, moving on from there, let's actually dive into one of these here. And actually, no, before we do, here's just kind of the step that we'll end with when we actually get to a full practice at one of these. We know how much energy is needed to hold this atom together, or this nucleus together, but often you may be asked for a binding energy per nucleon. What do you think per nucleon would mean?
Energy by the number of nucleons. Just like in
divide the binding energy by the number of nucleons. Exactly. Just like in math classes and even in elementary school, when you see that word per, you're dividing, and then you're dividing by the number of nucleons. So that's an important vocab word you need to remember, right? And exactly, Sarah, the energy each one of those nucleons needs to be able to be bound to that nucleus, right? So in this case, we know, of course, that the helium has 4 nucleons, and we can simply count 1, 2, 3, 4 if you have the graphic. So like I said before, there really isn't an equation for this, but your last step will always be to divide by the number of nucleons.
And we're going to do at least one example, and if we have time, we'll do 2 of them.
Okay. And we're going to do at least one example, and if we have time, we'll do 2 of them. But what I'm trying to show is that we're really just kind of converting the number to a more useful measure. Mass defect tells us a number, but we need to convert that to binding energy, which we haven't done yet, but we'll use that conversion factor to do. And that number maybe isn't as useful as knowing how much energy each of those particles needs, so that's what this third answer will be. So right, you'll end up dividing. I didn't write it very clear, but there's a division symbol. You're going to divide by the number of nucleons. And like I said, I have a flow chart to show you kind of step by step in case you miss a variable or get confused at all. So that chart should also help. And I think we might be ready to dive into that. So here's my little work of art. What you're going to start with, of course, is a given element and its nuclear mass. If that's not given to you, you're going to need to refer to a periodic table. And I've had a couple students take the Module 7 test already, and they did mention that they needed a periodic table, which I have posted on the resource website, and within the first couple lessons of Module 7, there's links to periodic tables. So you can either find one of your own or use one of the ones we're offering, but that's something that you will need as a reference. So don't forget about that. Then we're going to go on to just what we're used to doing back in the beginning of Module 7, figuring out the protons, neutrons, and nucleons, just kind of making that list. And then we have to figure out how much each of those weighs. So we'd find the mass of the parts. Once we know that, we'll calculate the mass defect. Once we know that, we'll find the binding energy. And once we know that, we'll find the binding energy per nucleon. So really the assignment that you'll see in 7-11 is asking for mass defect, binding energy, and binding energy per nucleon. Those last 3 boxes are basically what you'll end up having to find within that assignment for a different element. So I think let's go ahead and, let's see, I think I have one here. Okay, so we've already talked about helium already. Let's move on to another one here. Here we have lithium. So lithium-7 has a nuclear mass of 7.016005. And what I would encourage you to do is keep all these digits, even though they're a little annoying to go out to 6 places after the decimal. If you round to just like 2 or 3, it really is going to mess up your numbers. So kind of be particular about keeping all of the digits here. And let's see here. I'm going to open up a periodic table. Actually, I think I might have one a couple slides down.
So lithium is right here.
There it is. So lithium is, where is it? Right here. What does that tell me? I found it on the periodic table, but what good is that doing me? What am I pulling from that table that I'm going to need to know?
And really often, as far as we're concerned, we're really only going to get the number of protons because we're given an atomic mass.
And really often, as far as we're concerned, we're really only going to get the number of protons from this because we're given an atomic mass. So really all you have to look for is what the number is there in the corner. So this is lithium. It has a 3 there. And what does that 3 mean? A 3 what?
Remember that number that has to be particular to the element is a proton.
Right, 3 protons. Remember that number that has to be particular to the element is the protons. If we give the element an extra proton or take one away, we're totally changing where we are in the periodic table. So that number has to be 3. Now when they give you an element, they're going to tell you a number, and that number is a particular one too, and it's an important one because it could vary. This happens to be lithium 7. What does that 7 mean?
Don't confuse it with neutrons. Nucleons are all the particles. We could have some extra neutrons.
Right, 7 nucleons.
So,
don't confuse it with neutrons. Nucleons are all the particles, and we could have some extra neutrons. So
but it really is hinged upon
this could be lithium 8, and we'd be still kind of running through the same process, but it really is hinged upon this given. So they have to tell you this. All right, and then we can do the math, right? So we know if there are 7 nucleons and 3 of them are protons, that leaves the other 4 to have to be neutrons. Nice simple math for a Monday. I like when it works out that way.
Now what we have to do is figure out, well, what are the mass of all of our parts?
Okay, so that's easy enough. Now what we have to do is figure out, well, what are the mass of all of our parts? If I wanted to, if you're a visual person, you could easily draw this. And if you wanted to maybe draw it like this, you could. Draw each of your protons, draw each of your neutrons, and you have that number next to each. That'd kind of be the long way to write it out. Here in this one, they drew it with it kind of all bunched together. But basically, the key thing to remember is that if I have 3 protons, I'm going to multiply the 3 by the mass of the single proton. And then I have the 4 neutrons. I'm just going to make those yellow here. And then I'm going to take that number of neutrons times the mass of a single neutron. So that's, of course, the faster way to write it, rather than adding them one by one by one. Either way, you'll get the same answer. So I'm just going to, I think I'm going to type it so that my bad penmanship with the mouse doesn't get in the way. So, and I think a mistake I see here quite often is students will flip-flop proton neutron. So kind of take your time to look and make sure, okay, the protons were really 3. It's not going to mess it up by much, but it will mess it up if you accidentally put in the mass of the wrong one there.
What are you guys getting for that? Let's try to keep all of our digits.
Okay, and what are you guys getting for that? Let's try to keep all of our digits.
8135.
Austin's getting 7.058135. And that's in atomic units, so we just put a little lowercase u next to it. Anybody else get that? This part is probably more tedious and difficult. It's just making sure you didn't make any typing mistakes when you type in all the numbers.
Anybody else get that?
Anybody else get that? I haven't done this one in a while, so I don't have this answer memorized.
Okay, I'm getting the same thing. I'm going to keep going. That means I'm going too fast.
Okay, I'm getting the same thing.
I would label as
I'm going to keep going. Stop me if I'm going too fast. So this I would label as the mass of the part.
Calculate the mass defect. How do I do that?
Okay, now I'm going to follow my little flow chart here. Calculate the mass defect. How do I do that?
Subtract the nuclear mass from. So if you want to write
Subtract the nuclear mass from the mass of the part. Right, exactly. So if you want to write kind of a short version of it, it is the mass of the part minus the mass of the whole. So you might want to just write it very briefly as parts minus whole. 7.058135 minus 7.016005 and 0.04213 atomic units. Sounds good to me. And Theory, you have a question? You're good? It should always be a positive answer, so if you accidentally put them in the wrong order, just drop the sign, because really the mass of the parts is always going to be bigger, so you traditionally want to start with that number first. Okay, so that is the amount of mass that is unaccounted for, and we're basically saying that, Einstein's equation is telling us that there's an energy relationship there. That missing mass really is the binding energy holding this nucleus together. So here's where you can use just kind of dimensional analysis if you don't see whether you should multiply or divide. We have that answer of 0.04213. And we want to get rid of the atomic unit, the U unit, and convert it to mega electron volts. So basically what it's telling me is that one atomic unit is 931.5 mega electron volts. So does that mean I'm multiplying or dividing here?
Multiplying, right. And it will always be multiplying. I like to show with dimensional analysis, just to kind of
multiplying, right. And it will always be multiplying. I like to show it with dimensional analysis just to kind of prove it. This is a place where I see students accidentally divide, which gives very crazy tiny numbers. So, yep, go ahead and calculate that one. And you can leave the unit in mega electron volts. You don't have to kind of write that in scientific notation. So it's just a matter of taking the 0.4 or 0.04213 times 931.5 and getting a number for that. And that's 39.244095. And the units are mega electron volts. Okay. And one last step. And we're almost out of time. So now I want to find binding energy per nucleon. We already discussed how to do that. Anybody remember? What was the last thing that we said we would do?
So that's where we have to go back.
Right, here, exactly. Divide by how many nucleons. So that's where we have to go back really and remind ourselves. And that's why it's nice to kind of make the list. We know there were 7 nucleons, so it's just going to be the 39 blah, blah, blah number here. And that the digits going on forever is kind of annoying, but we'll deal with it, right? Divided by the 7. So that leaves us with 5.60. 6299 857 mega electron volts. So I know this number doesn't have kind of a personal meaning to it, but it's something that we can use to compare and see if there's any trend in the binding energy that's needed for, say, something like helium or something like plutonium. So it's kind of a value we can use to at very least make some comparisons. And that's what your last question will ask you to do within the assignment.